Our next speaker will be Nele Deckers. She holds a master's in civil engineering from the University of Leuven, and she has excelled in leadership roles in SCIA, including Director of Product and Design and Customer Service Manager. She currently serves as COO at Orion Lasertech, where she drives innovation and continuous improvement in laser technology. Passionate about people management, strategy, and innovation, she fosters growth and excellence. So welcome with me, Nele Deckers.
Thank you. Hello, everyone. My name is Nele Deckers, and today I will talk to you about the future of lasers, specifically in the glass industry. We believe in Orion that lasers will play a very important role in the coming decades, and I will explain you why we think that. So first, the overview, what I'm going to tell you. I don't know if you know Orion Lasertech. Are the people here that knows it? No? Well, I will briefly introduce in 2 slides what it is. Then I will explain the basics of laser technology, because that's something you need to understand why it's so interesting for glass. Then how you can use it in the glass industry, and then future potential. So who is Orion Lasertech? We are a company only doing innovation with lasers on machines. So we create laser machines for the glass industry and nothing else. So we make laser machines for cutting, for drilling, for everything that you can do on the glass. We have a large test lab available with a lot of lasers, optics, test engineers, and we have many installations all over the world. We are 56 employees at the moment. We have all competences in-house ourselves, so we make the whole machine. We have R&D specialists and laser specialists, but also engineers specialized in machine development, automation, electricity, everything in fact. And we have a very good customer care team. So that's very brief in a nutshell who is Orion. Now let me start with the fundamentals of laser technology. I don't know how aware you are about how a laser works, but a laser is in fact a light amplification by stimulated emission of radiation. If you compare that with classic light, as we saw just a presentation before, it's about all wavelengths in all directions, and all wavelengths are the wavelengths that we see are combined with a color. So we see a certain wavelength in a certain color. A laser works differently. Then you have stimulated emission, so you need a pump in the laser source to make sure that all photons goes in the same direction. You have one single wavelength per laser. All photons are moving in that same wavelength with perfectly aligned peaks, and they're all unidirectional. And those 3 things are very important, because then you have like one, you all know a laser light, a very thin light with a high energy on it, because all the energy is in that one little beam. So you can use that for different things, and you see it popping up all over the world in all different materials. This is the whole spectrum, and you see you have lasers in the visible spectrum, but also like the CO2 laser is completely outside the visible spectrum. So that's a laser you don't see. If it shines, you don't see it. What's also important, it's not only the laser continuously, but what's really also important is that you can have also pulsed lasers. So you pulse, you send out a pulse, and in general they're talking about a certain like 100 watt or 50 watt laser. That's the average power. You can also save up that power and just free out the energy at certain pulses. So the average is the same, but you have high pulses with very high peaks and very high energy that you send out. And then there is a difference between a long pulse or a short pulse, not only in the energy level, but also if you put a large pulse longer on a material, you can create heat effective zones, and you can create effects you in fact don't want to see on certain materials. If you have a short pulse duration, then you can neglect that or avoid that you don't have a heat effective zone, because it's so short that you just do it very quickly and you don't have those side effects. So that's a trade-off that you need to make with the laser. So what's important if you look at laser characteristics for any material, are the wavelengths is very important. You need a wavelength that will be absorbed by the material. If it's just reflected, it will do nothing. A pulse duration is important. What's the duration of the pulse? The power per pulse, the frequency of it, the quality of your laser beam. But that's, again, something you can also play with a bit with all the optics you're using. So the optics are important. And what's the effect on the glass? Well, you have multiple things you can do. You can heat the glass, you can melt it locally, you can ablate parts of it, you can ablate only the coating and don't touch the glass. So that brings me to what can we do with the glass, with lasers on the glass industry. So major topics are cutting, drilling, coating, removing, and marking. Let's start with cutting. Cutting, yeah, you can cut glass, you can cut all sort of glass. I think what's very interesting is that you also can cut curved glass with a laser. This is a laser machine we have in-house. You see here is the laser, and it can move in the beam like this, but you also have a rail there, so it can move in X and Y, but also in the height you can play with it. So there's also a height movement possible. And it's in a closed box, which makes it a classification 1 laser machine. That means no laser can come out of the machine. That's something that you definitely want. If you then look at how it works. Okay, so cutting, it's in fact 2 processes. First, you're going to filament the glass, so you make little holes in it or little scratched lines in it. And then you cleave it. Cleave, you can compare it with break it. That's something you can do by heating it up with a laser, for example, and then you can cleave the glass. And here you have a movie. Yeah, it's really cutting the glass, but it's an invisible laser, so you don't see much, but the glass is cutted. We tried the same by putting a white paper under it with black lines, and then you see it a bit better. So you will see that a crack will appear here. I don't know if you saw it. And then yeah, okay, now it's heated up and it's completely broken. And now my colleague will take it out. And that's 2 times the speed, the handling. And this handling is 2 times the speed, to give you an idea. Of course, you can also do that with a pick and place robot and then just pick the glass and let the scrap fall down. So what's really interesting about it, it's the very nice quality of the edges. No grinding is needed anymore. It can be fully automated. You don't need water. You don't have a dirty process. You can integrate quality control easily because you don't have dirty water or anything that creates problems. It's very reliable. So those are the benefits. For drilling, it's more or less the same, let's say. I hope my movie works. So, but then you're gonna drill. This is a green laser. This is very clear, I think. And here you see the process because the laser is visible. And now it's just drilling through quite thick glass here. And you see again that the edge quality is really nice. So it's not treated afterwards. And now you see the hole in it. So very good edge quality, and in fact the same benefits. So easy to integrate automation. You don't have water supply. You also don't need as an operator to change the drills, because if you need a bigger hole, you can just select that in the HMI. It's very easy. You can connect that to your ERP system and just make it fully automated. Then coating removal. You have the most common one is edge deletion, but I think the most interesting one, if we look at the future, is a 4G, 5G indoor connectivity. If you look at that, you have, in fact, coatings, low E coatings that are maybe not so good for the human being, but which can let the infrared, it will reflect the infrared, but let the visible light through. Problem is that it's not only reflecting the infrared, but also the wireless signals. So in new buildings, you often have a problem with your connectivity with your cell phone. The easy solution for it is, in fact, that you remove the parts of the coating, which will still filter out the infrared signal, but let the wireless signals through. So what you do is, in fact, you make a grid. Here you can see the laser working, and it will make a grid pattern on glass. This is a jumbo machine that we have in production at the moment. And then it comes out like this. So you have a glass with all rectangles on it. The rectangles are 0.06 millimeters, so very thin. The lines, sorry, the rectangles are 40 on 40. And yeah, it's not only rectangle. Yeah, we work together with the KU Leuven to test how good the connectivity is before we decode it and before and after it with different types of glass. And what we see is that not only rectangular forms are the most interesting one. You also have some call it turtle, some call it a giraffe, but an honeycomb is also possible. There are a lot of patterns possible. Here you see a train in Belgium. The upper windows of the train are decoded by our machines. So it's already for years like that, and then you have a good signal in the train. What's the difference if you would do it with general cutting? You don't have grinding marks because the laser will only touch the coating and not the glass. And then the last option I wanted to show you is bird-friendly glass. That's a hot topic in America. There are regulations already about it. Europe will probably follow. We don't know that yet, but okay. Bird-friendly glass is a hot topic there. So here you see, for example, a glass full of dots to prevent birds flying into it. You can play with all the dots. IGU units are possible to put directly on the machine and as last step in the process. And here you see different type of dots. I just wanted to show that the longer you laser on a dot, the more whitish it becomes. It's simple as that. It's more engraved. And then you can, for example, do it with a spiral. So here you really see a bit of a disc pattern. But here are just lines. So here it's more opaque dot. So you can play with a lot of things. Birds don't like reflective dots. So that's something that you also need to measure if you want to have bird-friendly dots. And here you have the machine working normally. Yeah. So you can see how it works. So here we have 4 heads. We can go up to 12 heads. And then, yeah, it makes dots, it jumps, and it makes the next 4 dots. Yeah. What's the future potential? So you can, in fact, input that laser on all kinds of machines. So you can put it as a jumbo glass. Our newest one is much thinner, to be honest, or horizontally. But you can also, and this is the biggest one of the 2 machines we are often building. This is for the automotive glass, but we also have a smaller one for more technical glass sizes, and there you have a pick and place system. And so at this moment, I only covered the basics. Those are the things that are already in the market, but we see smart buildings, a better connectivity. You will see an increase in that because connectivity is important and it will become more and more important in the future. Safer glass, 3D cutting of glass, bird-friendly glass. At this moment, it's almost only dots that you see, but we see also the change in there, that they come up with all kinds of patterns. Enhanced displays for electronics, switchable glass, optical innovations. A lot is possible. And why do we believe that lasers will be the future? Because of its precision, its sustainability, the efficiency of a laser. It's smarter and safer and has a smaller footprint. And you can customize a lot. So you can automate and customize a lot. Thank you for your attention. And if you want to reach out, feel free.
Thank you for your presentation.